So welcome guys. In continuation to where I actually stopped, I later got my x to be equals to 1 over n plus 1, which is the point that I just got at the turning point, like the point for the stationary point. Or this is the first stationary point I got as 1 over n plus 1. N actually ranges from 1 to infinity, right? N starts from 1 to infinity. So it can be 1 over 2, 1 over 3. So I got a particular stationary point here. So how will I know? Because I will need to consider this particular point I got. I think there are some that the previous example that we did, we got two answers, right, for x. So sometimes you usually get one, sometimes we have two points. So what's going to happen now is that I'm thinking of trying to explain how to consider that, okay, this is the maximum value for that point. And how will you consider the maximum value? You need to differentiate twice. That means you'll have to differentiate this function twice. Where is it? This is the first derivative. Then you still go ahead and differentiate this thing again. So if you now, after getting the second derivative, you now have to substitute x for 1 over n plus 1 and then confirm whether the result is less than 0. If the result is less than 0, then that means this particular 1 over n plus 1 is said to be maximum. And then you can go ahead and substitute it into this definition um, of uniform convergence, which says fn of x minus f of x is always less than the epsilon for given epsilon greater than 0. There exists n which is always greater than n naught, or you say n greater than big N. So I think that's just the definition in that case. Now looking at this now, that is if I don't want to show that this thing is maximum, because you still have to go and check for the second derivative. Let's say after finding the second derivative, you have some expression, maybe something over something, do you understand? And then after that, let's say you have, I don't know what it will be, but if you differentiate it twice, you surely get an answer. After getting an answer, let's say you have nsq, then let's say 1 minus x, something of this nature, and then it's being divided by something, or whether it is being added with something. So this is what I expected you to do. Now in this case, you have to substitute this 1 over n plus 1 into this second derivative, 1 over n plus 1 cube in this case, and then decide to set your n to be equals to 1. Start from 1, set your n to be equals to 1 in that case, and confirm whether the final result will be what? Less than 0. If the final result is less than 0, automatically speaking, then we say that this x equals to 1 over n plus 1 is a maximum value. And we used to consider the maximum value most of the time for this expression here. So, okay. Now, looking at this now, I will just decide to, instead of going through all this stress, I already take this to be maximum. I can also show it in another video, but just take note that it will really take your time for you to fit it twice. So in this case, now that means I will look for fn of my x is 1 over n plus 1 in this case, right? And then minus the pointwise convergence is 0, is less than what? I don't know. So my fn of x is given to us as nx open bracket. Let me check it. What's my fnx? That's n squared x, then 1 minus xn. N squared x, then 1 minus x raised to the power of n. Then this is what I have as my fn of x. This is my fn of x here, right? Then minus 0 is less than epsilon. So if I set my x to be equals to 1 minus 1 over n plus 1, that means I will have n squared. This x is already 1 over n plus 1. Then I will have 1 minus 1 over n plus 1, then raised to the power of n. You having this kind of expression, minus 0, I have this. Is it less than epsilon? So let's check. So I have n squared times 1 over n plus 1 times 1 minus 1 over n plus 1 raised to the power of n. I already took this to be 1 over 2. Now looking at this expression here, let's say we take our n to be equals to 1. Let's say we take our n to be equals to 1. So what's going to happen in this case? So if you take your n to be equals to 1, I will have 1 times 1 over 2, then times 1 minus 1 over 1 plus 1, that's 2, raised to the power of 1. So is it less than 1 over 2? Let's confirm. If it is true, then no problem. Then here in this case, I will have 1 over 2 times this SCM is 2. I should have 1 over 2 here also, right? And that's 1 over 4. So the question is 1 over 4 less than 1 over 2? 1 over 4 in decimal, that is 0.25. This is 0.25. And this is, in this case now, here in this case, it is 1 over 2, I think that is 0.5 in this case. Yeah, that should be 0.5. That should be 0.5 for this. That should be 0.5. I have this as k as n, then I have this as 1 over n. So I think this is what I actually have as the result. So this result here, I think it is valid, right? Since I already have n squared, I still want to confirm. I have n squared x, and I have 1 minus x is power of n. If I substitute this as 1 over n plus 1, okay, this is what I should have. So now that I use 1, it is true. It is true for 1. It is true for when n equals to 1. But what if n when n is equals to 2? Is it going to be true? I'm very sure it is not going to be true. 2 squared is 4 times 1 over 2 plus 1 is 3. Then 1 minus 1 over 3. N is 2, right? Is it less than 1 over 2? Try this and you see that it is not equals to 1 over 2. So if I use my calculator to evaluate this right left hand side now, 4 times 1 over 3, then times 1 minus 1, it keeps increasing, then squared, then squared. I have it as 0.5925. Is it less than 0.5? You see, it is absurd. Since this is wrong for n is not true, that means it's not true for all the range of s given to us. So you don't just try for one and say it is uniformly convergence. Since it's not true for two, then what happens? Then we can actually conclude that s for a given epsilon which is equals to half or epsilon greater than 0, we cannot find a natural number n that's greater than n naught that which satisfy this definition. So we can't find it. So that's how it works in that case. Okay, that's how it works. Thanks for watching.